Hey everybody, welcome back. Let's look at some more trig integrals, this time some definite integrals, integrals with bounds. Okay, so here we have the integral from 0 to pi over 4 of cosine cubed of 2t dt. First thing I notice is that odd power. Let's go ahead and knock that down by 1. So I can think about this as the integral from 0 to pi over 4 of, let's see here, so cosine squared of 2t, but to make that legal, times cosine of 2t. So together that does make cosine cubed, so we're fine there. And my ultimate goal here is to use a u substitution, so it'd be nice to have some sort of sine cosine combination because they're derivatives of each other, right? So I think it's going to be useful if we recall the following. So let's go ahead and recall that for all theta, this is true. Sine squared of theta plus cosine squared of theta is 1, because we can use that to replace this. So we can replace this and just call it 1 minus sine squared of 2t. Let's go ahead and do that. So we're going to use a Pythagorean identity here and replace this. So we've got the integral from 0 to pi over 4 of 1 minus sine squared of 2t. And then we still have that factor of cosine of 2t dt. So that seems super promising because we can let u equal sine of 2t. And then we find du, of course, by taking the derivative carefully. Now here we need the chain rule. So this will be the cosine of 2t times 2, of course, dt. Now don't forget we need new bounds. And so for my new lower bound, so how do we get new bounds? You just remember that these correspond to t. So just plug this lower t value in for t here. And that'll tell you your new lower u bound, right? So that'll be sine of 2 times 0. So that's sine of 0, which is 0, of course. And then my new upper bound, I plug this t value in for t here. So that means that u is equal to, let's see here. Well, if I double pi over 4, that's pi over 2. And we know, of course, that's 1. Okay, this is promising. Oh, one thing I usually note that I think I forgot here, that's fine though, that if we solve, that's 1/2 of du is cosine of 2t dt. And that's important because that allows me to replace this, right? This could be replaced with that. So I've got 1/2 the integral from 0 to 1. This is going to be 1 minus u squared, so 1 minus u squared. And we said that this was taken care of by that 1/2 of du. So that's really nice, and you can see the power in the substitution that we took something that looked maybe a little bit tricky, and with a little bit of legal algebra and a substitution, we turn into a much nicer integral. And so it looks like we just want to use the power rule here. So this will be, let's see, antiderivative of 1 is u, antiderivative of u squared is u cubed over 3, and we want to evaluate from 0 to 1. Okay, so that seems pretty good so far. And we'll just go ahead and finish it out. And again, you want to notice when I change the bounds, I don't go back to my original variable. All that info is encoded in the bounds. So you're just solving this problem. So once you get to this point, just solve this and forget everything else because this is equal to the original problem. Okay, so by the fundamental theorem of calculus, I plug in 1. I know that'll vanish at 0, but I'm still going to maybe show it. Okay, so that will vanish. That's 1 minus 1/3, which of course is 2/3. So I get 1/3 as the value of the integral. Okay, so yeah, hopefully that made some sense. Let's go ahead and try another one. Now in the next one, we're gonna have a couple options. So maybe I'll star this one because There's a bunch of different ways we can go about tackling it. So this is the integral from minus pi to pi of sine squared of x times the cosine squared of x dx. So I'm going to write options. I'll solve it one way. You can go ahead and try it another way. So I'll say option number one to solve this is to make the following realization, right? So this is to use the power reducing formulas which come from the double angle formulas. And that's to realize that both of these can be rewritten. So we know that sine squared of x is equal to 1 minus the cosine of double angle over 2. And then we know that cosine squared is just the conjugate of this, right? So cosine squared of x is exactly 1 plus the cosine of a double angle over 2. So that's option one, right? You'd replace both of those, multiply them out, and then you'd have to use a power reducing formula once more, and then you could solve it just fine. Option two, let's see here. Option two is to use maybe the double angle formula. For sine. And I think no matter which of these you choose, ultimately you will have to use a power reducing formula. It's just here I think you'll have to use it 2 or 3 times, and here you'll just have to use one of them. So remember that sine of 2 theta, perhaps, is equal to 2 cosine of theta sine of theta. Now, you might be saying, why is that helpful? And that's a good question. You just want to look here and realize that you almost have a form like this. If you divide both sides by 2, so you can say that sine of 2 theta over 2 is equal to cosine of theta sine theta, which of course is the same thing here as sine theta times cosine theta, right? Multiplication is commutative. If you square both sides, you'll have something that looks like this, right? If I square both sides, so if I square the left side, it's going to look like this. Okay, so that's me squaring the left side. And if I square the right side, I have something that looks like this. That means I can replace this quantity, which is right here, but with x's. I can replace that with this, just write it in terms of x's. So let's use this. So I'm going to use the double angle formula. So here we have the integral from minus pi to pi. Sine of 2 theta over 4 d theta. Okay, so I could use properties of even functions here if I wanted to. So just let's recall the following from single variable calculus. So let's also recall this. So recall, if f of x is a continuous even function, so that means it has y-axis symmetry. So if f of x is a continuous even function on some symmetric interval AA, or minus AA, then the integral from minus a to a of f of x dx equals 2 times the integral from 0 to a of f of x dx. And quickly, why does that make sense? So let's see here. So if f has y-axis symmetry, so for example, let's say here's a, and here's minus a, so do pretend that is symmetric about the y-axis. Well, if f has y-axis symmetry, that's what it means to be even, then it means that this quantity, which is represented by this integral, is the same thing as computing this quantity and then just doubling it. So intuitively, that should make sense. And we can actually use that here because, well, sine by itself without the square is an odd function, right? But the square makes this now an even function. So using the property that I just mentioned, we're going to have 2 times the integral from 0 to pi of sine squared of 2 theta. And then this over 4, I'm just going to bring that outside like this. So that was using that symmetric property of even functions. If you don't want to use that, that's fine. You can just compute this all together. And so now the question is, okay, well, I have a purely even power of sine. How do I integrate? Well, it turns out here's where I'm going to need the power reducing formula. So I want this, but what's playing the role of x for this? Playing the role of x is 2 theta. So for x, I just need to plug in 2 theta here and here, and I'll have a replacement for this. So again, this is playing the part of x. So I plug this in for x both here and here, and that gives me a replacement of this by this. So what should I get here? It should be 1 minus the cosine of 4 theta. Right, this always doubles. Whatever this is the double of that. So that makes sense that that's 4 theta. Right? If I double that, I get this. This will be over 2, which I can bring out in a moment, d theta. So that's pretty promising. That seems really, really good. So let's factor this out. So we're essentially factoring out a 1/2 here. So 1/2 times 1/2, that's going to give us a quarter. We have the integral from 0 to pi. This is 1 minus the cosine of 4 theta d theta. And now we can just directly integrate. So the antiderivative of 1 in respect to theta is exactly theta. Here I'm going to use what I like to call the anti-chain rule. So it'll be antiderivative of cosine, or antiderivative of minus cosine is minus sine. You can think about it that way as well. Same angle or same argument. And then I need to multiply not by the derivative of the inside, but by 1 over the coefficient of theta. That needs to be there because if I check my work carefully using the chain rule kicks out a 4. Those would need to cancel so I could recover this. And now we can just evaluate. So both of these will vanish at 0. So something to look out for. So I plug in pi. And if I plug in 0, that's going to be 0 minus 0. Now, sine of 4 pi is the same thing as the sine of 2 pi, which is the same thing as the sine of 0, which is 0. And so all I'm left with is pi over 4. And that's the value of our integral. Okay, so for the next one, I think we should try one involving tangent and secant. Let's go ahead and try that. So let's look at the integral from 0 to pi over 3 of tangent of x times secant to the 3/2 x dx. And there's a couple things I want to note here that'll probably be helpful. It's going to be helpful to note the Pythagorean identity here. So tangent squared of theta plus 1 is exactly secant squared of theta. And I noticed this upper bound of pi over 3. So I really want to have that triangle that has pi over 3 in it. Remember, this triangle comes from half of an equilateral. If I take an equilateral triangle and I drop this altitude, it gives me exactly this right triangle. So here's pi over 3. Here's pi over 6, because again, if I start with an equilateral and that's an altitude, this angle's bisected. And let's say this is 1, 2 by Pythagorean theorem. This is the square root of 3. So that'll be helpful for evaluating at some point. And so let's see here. Okay, so maybe let's go ahead and move a tangent and secant to the right here. So tangent of x times secant to the first of x dx. I know that's the derivative of secant. Well, so what's left over if I do that? I'm still going to have, it looks like a secant to the first. Let's see here. Well, not to the first, right? Because I want the sum to be 3/2. So that should definitely be 1/2. Yeah, so 1 plus 1/2 gives me the 3/2. So that seems strong. That sets us up for a substitution. Let's let u equal secant of x. And then the derivative, of course, is the product of secant and tangent, both of x dx. And I'm going to want some new bounds. Here's where this triangle will help with the upper bound. So new bounds. Every time you switch variables, switch those bounds. So for my lower bound, that's an x value. So looking at my substitution statement, this will be u equals the secant of 0. Oops, secant of 0. But that's exactly 1. If secant bothers you, just remember that it's the reciprocal or the flip of cosine. So you can just take the cosine of 0 and flip it. That's also the secant of 0. For the upper bound, pi over 3 goes in for x here, and I use my triangle to help. So for my upper bound, this is secant of pi over 3, which means you could just take the cosine and flip it. If I took the cosine, it'd be 1/2. If I flip it, well, when I flip cosine, that's exactly what secant is. So that's 2. So it looks like I'm integrating from 1 to 2. So this is exactly du. That's really nice. And this is exactly u to the 1/2. So that means we can just go ahead and use the power rule. So really, really nice. So that's going to be, it looks like u to the 3/2. And then dividing by 3/2 is the same thing as multiplying by 2/3. Okay, so that's the power rule for integration. I'm going to rewrite that just so this works out a little bit better algebraically. So how about 2/3? What about the square root of u cubed? You can write the cube there or there. That doesn't matter. They mean the same thing in math. Okay, so let's see what we have here. So we've got 2/3. The square root of 2 cubed minus 2/3 square root of 1 cubed. Now, the square root of 2 cubed, like I said before, that's the same thing as the square root of 2 cubed. But that's exactly the square root of 4 times 2. So that's 2 radical 2. So that's exactly 2 radical 2. And this is just going to be 1, so that'll be 2/3 times 1, so that's not bad. Again, you could factor the 2/3 out if you want. You could leave it. It just depends whatever your professor prefers. Just go by that. That's perfectly fine. So if they prefer to multiply it out, you can deal with common denominators if you want. That's fine. Or this right here, this is really bad notation to write like this on the side like that. Maybe I'll put this underneath. I just want this clear chain of equalities. I think that's a bit better. Or if I factor out of 2/3, that would be just fine, right? So I could factor out of 2/3 and I can say, oh, well, that's 2 radical 2, right, minus 1. That'd be fine as well. Again, it just comes down to preference at that point. Yeah, so hopefully these examples of trig integrals help. And leave a comment down below. Let me know. Did they help? Any requests? Let me know.